Can you guys hear me in the back? Awesome. All right. So I'm Gareth. I'm a postdoc over at the Kavli Institute next door, and today I'm pretty excited to be able to tell you guys about merging galaxies in the local universe and how they compare to galaxies in the local universe that are merging. So first of all, of course, if you're talking about the early universe, you have to go through the entire history of the universe, which, once I turn this on, we'll be able to do. Right. So, in the beginning of the universe, there was the Big Bang over 13 billion years ago. Right after that happened, everything was a hot ionized plasma, and nothing could really collapse in on itself. Eventually, stuff expanded. The ionized gas was able to form atoms, and then light could escape from that. And then after that, everything was a little bit darker, but there weren't any stars yet, because nothing had collapsed to make stars. So that was the cosmic dark ages. And then as the gas cooled down, it started to collapse in on itself into gravitational wells. It started to form stars, and these stars started radiating and forming galaxies. So when we talk about the early universe, we're mainly going to be talking about from the first galaxies that formed through to around 1 billion years after that. So that's a lot of words, but I have, I think, 3 or 4 videos to show in here. So these are all simulations. So this is a simulation from the Illustris suite, which took a giant block of space, filled it with gas, and then let it run from the very early universe. So this is 12 billion years ago to the present day. And this plot is colored by gas density. So the white is very dense gas, the bright orange is as well, and then later on you'll see black and purple, which are not as dense. So start that off. The first thing you'll see is that the gas isn't just falling into a single sphere or anything. It's collapsing into these long, thin features called filaments. And that's where most of the stars are going to form. And when 2 or more of these filaments intersect, that's where you get these giant star clusters, or galaxy clusters, sorry. And also the gas in galaxies kind of flow inwards towards these clusters along these filaments. So each of these little points of light is actually its own galaxy. So this scale up here, 900 kiloparsecs, is 2,700 light years. And that's changed, so I can't really explain it. But our galaxy is only around 20 kiloparsecs wide. So these are really big simulations. And this one was actually made to represent a formation of a supercluster. And we are roughly 10 billion years from the start. Here we can see that there's a whole bunch of galaxies, and we have the 2 superclusters there. But yeah, there's a whole lot of different scales, and all the gas was colliding in on itself. So that's if you have a giant cube just filled with gas. So now we're going to look at just 2 galaxies that are colliding. So on the left is going to show the stars, the optical light, and the right will show the gas. And the gas will be colored by what it is. So the pink is kind of not that dense. Eventually the green will be hot gas. And I'll start this so you can see. These should be roughly aligned. All right, so these are 2 galaxies that will pass by each other, gravitationally interact, and then kind of bounce back and eventually merge. So you can see in the stellar portion, the stars in the disk don't really get that affected. You do see these extensions off to the side, which we call tidal tails. But in the gas, the distribution is much more extended and disrupted by each of the mergers. So on the second pass, you see that the ionized halo here will actually expand a lot, and the 2 galaxies will merge into a single rotating disk in the center, which you can see much better in the stellar component. And this tidal tail here actually lasts for a pretty long time. It's really extended. And the stellar simulation goes on for slightly longer, so you can see that rotating. And the dark region here is dust, which is pretty much anything that's not gas, which basically just means ash from the formation of stars. So yeah, it just keeps running. So eventually, we started off with 2 galaxies, and now we just have 1 galaxy with a giant halo of hot gas and a pretty extended stellar component there. Cool, so those were simulations, so you might be thinking, well, how does that actually compare to observations? So this is a video of a simulation of two galaxies colliding, and it'll be compared to Hubble images of galaxies. So if we start this off, two galaxies are pretty well separated, and as they come together, compare them to Hubble, and it's a pretty good match. And as these continue to get closer and closer, they're going to gravitationally interact a little bit. So the two disks are actually intersecting each other at this point. Rotate a little bit. So what's cool is that we can explain so many of these images from just a single observation. Or, sorry, a single simulation. We can explain observations with simulations of two galaxies merging at different angles and different times. So here you can see the two filaments that are coming out, and the two nuclei in the galaxies are still pretty far apart. As we rotate to look down one of the filaments, we're going to compare this to another one, and that's a pretty good match. And then the two cores will continue to come together, and I think there's one more in here, so we rotate that way. So if we see the two galaxies face on, we have that nice S shape from the tidal tails. But here we just have a straight line. If you just saw that image just by itself, you would think that's not a merging galaxy, but simulation suggests that it actually is. So yeah, that's about Space Telescope Science Institute in the US. Pretty cool. Right, so that last video showed you that local galaxies, we have a whole bunch of amazing images, mostly made by Hubble, of these mergers, and they all kind of show different morphologies. So like up here we have two galaxies that are just about to collide, basically. Galaxies that have rammed into each other and are in the process of merging. We have the antennae galaxies down here that have a bridge of dust that's connecting them, and then the tadpole galaxies where you see those big tidal tails that we talked about before. So locally we have amazing simulations, we have amazing observations. But what about the early universe? Well, it turns out that it's really hard to actually see what the galaxies are like. Sorry, I'll answer questions at the end.
Can you put your microphone back on?
Oh, is it on? Oh, sorry.
When your hand went down, it got switched off.
Oh, that'd be bad. Is it better if I just project a little bit? Okay, sorry, I'll project more because I don't know how to turn this back on. And Matt's gone. Okay, so galaxies in the early universe were kind of hard to see. So to explain why, imagine putting actually don't imagine, just put your thumb out at arm's length. So your thumb is 2 degrees wide on average, unless you have really long arms. So imagine dividing your thumb into 7,200 pieces. So that is the width of one of our galaxies. And it's so small, it's what's called an arc second. So an arc second is 1/60th of an arc minute, which is 1/60th of a degree. It's not 1/60th of a arc hour, which I think it should be, but that's my own opinion. Which means that arc second is a tiny fraction of a degree. So these are really tiny galaxies. And so as another example, let's say that this entire screen here is 1 degree. Then that means the moon is around half a degree, so it'd be that large. Of course, you know, when you look out in the sky, the moon is much smaller. But on this scale, a single arc minute would be that large, and I couldn't actually fit it, but a single pixel would be 5 arc seconds. So imagine fitting 5 of these galaxies into that single pixel, and then remember that really this 1 degree is half a thumb, so you have to shrink the entire thing down. Arc seconds are itsy bitsy, tiny things. And on average, we have to see a galaxy that's only that wide. So we mainly do this with, we can actually do it with Hubble and other telescopes, but the one that I use the most is the Atacama Large Millimeter Submillimeter Array, or ALMA, which is a set of set of telescopes in the Atacama Desert in Chile. So one of the main things that differentiate this from the Hubble or other telescopes is that they observe in the submillimeter instead of the optical. So optical wavelength is around 500 nanometers. Wavelength here is 1 millimeter, so it's around 1,000,000 times less energetic per photon. And in addition, instead of a single telescope, we have on the order of 40 of these, I call them satellite dishes, but parabolic antennas, I guess, that are spread out across a few kilometers of the desert. And using a process called interferometry, we can actually use these telescopes to simulate a single telescope that is the diameter of a baseline or a distance between antennas. So since these are separated over 16 kilometers, we can imagine, or we can simulate having a single antenna that's 16 kilometers wide. So using that, we can get some pretty good images. So these are not going to be as pretty as the ones from Hubble, but these are 4 sets of merging galaxies in the early universe. So starting off with big 3 dragons, this is seen as it was only 730 million years after the Big Bang. So really early, it's one of the first galaxies. And I had to Google it, but big 3 dragons is actually the name of a hand in Mahjong. So it's 2 objects, but it's called big 3 dragons because it's a really cool source. I think big 3 dragons is good. So yeah, he named it that. But yeah, this background image here, the color, the red, yellow, and green is from Hubble. So before those really pretty pictures, this is the same pixel scale, but here we're just really zoomed in. So you can probably, I'm not sure if you can read it, but this black bar is 1 arcsecond wide, which we know is very tiny. And as we look at these other ones, these are all in arcseconds as well. 5 arcseconds there, 1 arcsecond. So these are all very tiny. Next up, there's WMH5, which is an object I looked at, which is 2 galaxies that are colliding. Favorite object, Deimos Cosmos 818760, is 3 objects that are all colliding. And from looking at the velocities, we can tell that these 2 brighter guys, or I should mention here that these contours are kind of like a topographic map. So the more contours surround an area, the brighter it is. You can think of these as like mountain peaks of intensity. So these 2 bright regions are actually 2 galaxies that are colliding, while this 3rd peak is a smaller galaxy that will collide with those later on. So if you want a really terrible artist rendition, it's like, merger going on, another one that will happen in the future. And then a really cool object is W2246, where we have a single core galaxy at the center, and then these filaments of warm gas, and then some other objects all surrounding it. And as we saw from that orange simulation I showed at the very beginning, we expect these early galaxies to to be in a filament of gas and to have a whole bunch of clumps that are colliding with the galaxy and floating around it and everything. So this is kind of what we expect. But we can also look at more simulations in the early universe. So this is a simulation done by a team in Pisa, in Italy, where they took a big box and gave it some initial conditions in the early universe, evolved it for around 1 billion years. For here, GYR is giga-year, or billion years. And at each time step, they tracked the density, temperature, pressure, and chemical abundance of each particle. They accounted for star formation and the effect of radiation or light on everything. And they found that the gas collapsed in a filament, as we saw before. And they found a single galaxy inside that was larger than the other ones. Zooming in on that, zooming in on that. There's a single galaxy which they call Dahlia, which I had to Google this too, is a flower. Don't know much about flowers. And so this galaxy is only 1 billion years after the Big Bang, and it's actually surrounded by 20 clumps of gas, or small galaxies. The definition is kind of hazy at this point. Let's just say 20 clumps of gas that are actually orbiting this single object. So instead of looking at an evolution of a galaxy in a big environment, we can look at an evolution of a galaxy just kind of by itself for the most part. This was the same team that looked at a galaxy called Althea, which is also a flower. I have no idea about that. Which they let it evolve for around 200 million years in the early universe, where the time evolution is from left to right, from top to bottom. And the evolution here is pretty weird. It's a really disturbed, kind of messed up galaxy where it's not just a rotating disk galaxy like you would expect the Milky Way or Andromeda to be. It's got these weird collisions. It's not all in a single plane. It's all kind of colliding with itself. There's a merger with another galaxy that collides with it at one point. After that, it actually does kind of relax into a single spiral disk. Then directly after that, it gets disturbed again. So basically, these two simulations are showing that these galaxies in the early universe were evolving by colliding and merging with gas clouds and galaxies. So kind of as a summary here, there's a midpoint summary, I guess. So in the early universe, we have amazing images of galaxies that are undergoing mergers, and we have amazing simulations that match pretty well with what we see. So there's a pretty good concordance, good agreement there. But in the early universe, we have simulations that are of comparable quality. We can see down to really amazing scales. But in order to see if these simulations are right, we need to actually compare them to observations. And our observations are kind of behind at the moment, as we saw before. But it is kind of amazing because we are looking at tiny scales. But in order to actually see if our simulations and our theory agree with our observations, we need new observations, which means we need new telescopes. So in the future, there's a few telescopes coming out in the next 50 years, 30 years, that are pretty exciting. I think the one at the top of most people's mind is the James Webb Space Telescope. And if you were here for a talk by Emma Curtis Lake like a month ago, you probably learned all about this. But the JWST is kind of thought of as the successor to the Hubble, although really it's kind of different and better in different ways. So first of all, it only sees from the red side of visible light down to infrared, where the Hubble goes through all of visible light. And also, it has a much larger collecting area. And if you have a larger collecting area, you can get more photons, so you can see fainter things. So, and also red light in the early universe, or this infrared light, comes from warm gas or warm dust. So we'll be able to see really faint warm dust in the early universe, which is what we need in order to figure out what's going on. There's also the extremely large telescope, which is very creatively named, which is, I think, 39 meters in diameter. It's going to be another optical telescope. It's going to be amazing. And I don't even know if you can see it in the pixels, but there's a human being right around there. So it's going to be a giant instrument. And then the one that I'm most excited about is the next generation VLA, next generation very large array. And it's kind of nice because every time that they write this title officially, they use the next generation font from Star Trek. So the original Very Large Array was a set of 27 radio telescopes, where radio just means they're looking at kind of weaker energy photons than sub-millimeters, so kind of at the extreme edge of lowness of energy. And they had 27 of these radio dishes, satellite dishes, basically, out in the desert, and they could extend them out to 12 kilometers. And as we said before, using interferometry, we can simulate having a 12-kilometer wide antenna. Pretty cool. Except for the next generation VLA, they're going to expand from the original 27, which was green, to a more extended compact array. And then they're going to expand from that into a big spiral. And then they're going to go from New Mexico over to Arizona, over to Texas, down into Mexico. And it takes 12 hours to drive from there to there. So I mean, this is kind of a big scale. So they're going to go from around 12 or 36 kilometer baselines or separations to, I forget the number, I think it's 2,000 kilometers? 1,000 kilometers. So it's going to be way bigger. They're going to go from 27 to over 200 antennas, which means more collecting area. So they'll be able to see really small, really faint things in the early universe. And also the main side point is that the main science goal of this is actually to look at the formation of planets. But I care more about galaxies, so that's that. And also, so in addition to these new instruments and other ones which I haven't mentioned, there's going to be more observations with current instruments like ALMA, which I mentioned, Hubble, which is really amazing, and Very Large Telescope, which is the forefront right now. And also more simulations are being done all the time, and they're only improving. So this is the second to last slide here. Went a little bit fast. Oh well. So in case you think that galaxy mergers are something that's far away, never have to worry about them. If you are immortal, then you'll encounter a merger in 4 billion years, because the Milky Way will collide with Andromeda. So this is a it was a simulation done to see what it would look like from Earth when the two galaxies collide. So right now, Andromeda is really far away. In a billion years, it'll get closer. 3.75 billion years, it'll get closer still. Then right after that, the two galaxies will collide. And as we saw before, galaxy collisions and mergers are really messy. A whole bunch of gas gets thrown out. These red regions are where there's a whole bunch of new stars being formed because the gas gets compacted. If you look at 3.9 billion years, it's just messy. It's beautiful. But also around this time, the sun will go red giant and will be kind of inside the photosphere of the sun, so we'll all be dead. But I guess we'll be dead anyways. But your 10 to the 8 great-grandchildren will see this. So in 5 billion years, we'll just have the two nuclei of the Milky Way and Andromeda separated, and then 7 billion, they'll be just one. So these mergers do occur in the early universe more often, except they will actually affect Earth one day, or maybe not Earth, but our solar system. Cool, so these are the conclusions here, and I just want to, in case you actually love mergers as much as I do, just want to shout out to, if you go to tngproject.org/media, you can go to the illustrious media gallery. So that first simulation I showed, called the orange and white, was from there, and they have a whole bunch of other simulations of single galaxies evolving, amazing images, a lot of good work. There's also those pretty pictures that I got from Hubble, or from spacetelescope.org/images, and they have a whole bunch of other galaxy mergers and just really amazing pictures that make my images look silly. And also, if you use Steam and you want to play a video game that does science, you should get Universe Sandbox, or actually Universe Sandbox 2, where you can have multiple galaxies and planets and stars and let them evolve and orbit and collide. And my title slide and each of these was actually made in Universe Sandbox, and no one really notices. They think they're all actual simulations. So that's a pretty good thing there. Cool, so that's all. Thanks for listening.